everyone. In this video, I'm going to be discussing the idea of density, which in chemistry just means a measure of how close together particles are packed. As you can see from these two models on your screen, if we envision each of these paper clips as atoms of a particular element, we'll note that the model on the left represents a material that's much more dense than the one on the right, simply because its particles are closer together. We can represent that mathematically using the equation that you've seen many times before in science classes, that density is a ratio of mass over volume. If we take a look numerically at what this means, we can start making predictions about how much mass a particular element will have or how much volume it will take up, given a certain set of circumstances. For those types of calculations, you're going to need table S. If we look on table S, what you're going to see is that each element has unique density. Elements that are gases at standard temperature, things like hydrogen, oxygen, fluorine, they have extremely low densities because you know that gases have particles that are spread very far apart. If you look at elements that are solids at standard temperature, things like titanium, cobalt, nickel, and copper, you'll see that their densities are much higher because you know that solids have particles that are packed more closely together. So for our two models, I'd like to envision that the one on the left was, let's say, zinc, with a density of 7.134, and the one on the right might also be a solid, but one with a little bit less density, maybe magnesium, with one of 1.74. Let's keep those values in mind and do some calculations. If we go back to our models, what I notice is that this one here on the left, if I have 8 of these quote-unquote atoms, it only takes up this much space. However, here on the right, the same mass, perhaps, takes up substantially more space. We can actually measure that precisely given a particular density and given an initial starting mass. So again, let's pretend that this element here on the left is zinc. Zinc has a density of 7.134 grams per cubic centimeter. We know that's a ratio of its mass per volume. So if we just go ahead and say that this sample weighs 8 grams, we can calculate exactly how much space those 8 grams of zinc would take up. To do this, you can use some algebraic manipulation, or if you'd like to just cross-multiply, we can throw the 7.134 over 1 and take note that 8 equals 7.134 times the volume, which means to solve for the volume, I'm going to need to divide each side by 7.134. I'm going to let my calculator do the work for that, and what I'll find is that the amount of space this particular sample of zinc will take up is about 1.12 cubic centimeters. Notice that I didn't include all those decimal places. In chemistry, you can typically round to the nearest 10th or 100th, but we'll talk about that more specifically later on in the year. If we move over to this side and assume that this particular solid is something like magnesium, which has a different density than zinc, we can prove mathematically that it will take up more space. Let's plug in the numbers. Magnesium has a density of 1.74 grams per cubic centimeter. And again, if we assume that it has a mass of 8 grams, I can find how much space that 8 grams of magnesium is going to take up. Again, I'm just going to put this over a 1 so that I can easily see that 8 is going to be equal to 1.74 times the volume. To solve for volume, I need to divide each side by 1.74. And again, I'll let my calculator do the work for that calculation. 8 divided by 1.74 is going to give me a value of 4.5977. So I'm going to round that to 4.60 is my volume. Again, units of cubic centimeters. Comparing these two numbers, it's easy to see that the denser material takes up less space when you have equivalent masses. So you can manipulate this equation in whatever way you need to, as long as you plug in your variables in the right place to show relationships between density, the amount of mass, and the amount of space a particular sample will take up.